So in the first two lessons, we built the fully connected network, but the weights were set randomly and we didn't know of how to optimize the weights. So to make sure that the weights are optimized and the output that we are getting is closer to the actual value, we need two more things. One is the loss function and second is the optimizer. What is a loss function? A loss function is one that measures of how good the network's predictions are, and the optimizer can tell the network of how to change weights. So these two are the most important things. So if you think about it very intuitively, the model predicts something, but the actual value is something different. So, what is the difference between the predicted value and the actual value? The more closer it is, the actual value to the predicted value, the better is your prediction. But we need a function which would help us to determine the difference between the actual value and the predicted value. So for regression problems, a common loss function is a mean absolute error, which is the MAE. So here's the MAE and it shows, and what is it? It is the y true minus y pred, the actual value minus the predicted value, and we take the absolute difference. There are many other loss functions which you can explore. There is a mean squared error, the Huber loss, which are available in Keras. Now next comes the stochastic gradient descent, quite a mouthful, but it is not very difficult. What it does that it trains in steps. So one step in the training looks like this. There is a whole training data. You sample some training data and run it through the network to make predictions. The next step is that you measure the loss between the predictions and the true values. And then you finally adjust the weights in a direction that makes the loss smaller. So these three things are there in the optimizer for the stochastic gradient descent. Now, you will come across these terms quite happen. What is a mini batch? Each iteration sample of the training data is called a mini batch, while a complete round of training data is called an epoch. Why is the epoch different from the mini batch? Because what you are doing is that you are taking the training data, you are breaking up into samples, and each, to cover the whole training data, you require a number of steps. So that is why this concept is there, that there is a mini batch and there is an epoch. Now, while you train the model, one very important factor is that um, the batch size and the learning rate. So the batch size is the size of the sample of the training data that you are using in training. That is number one point. And another is learning rate. The learning rate is the weights needs to be changed, right? So how quickly are you changing the weights is determined by a factor known as the learning rate. Okay, so these two factors are there. These are very important, and this will help in getting the network very well. So when you define a model, you compile it with an optimizer. The most common optimizer which is there is Adam, and then you compile it with a loss which is the MAE. Now, let's look at an example of the red wine quality. Here, the input is this, and all these factors are the inputs: the fixed acidity, volatile acidity, till alcohol are the inputs, and what we are predicting is the quality. So what we do here is that we have a fully connected network, and what it is doing is that how many neurons are there. So it is 512 into 3, so that makes it over 1500 neurons are there. Another thing is that how many inputs are there. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 inputs are there. Okay. So that's why the input shape is 11. There you go for 512, and then it is a 3-layer network. So you repeat it, and the last layer is a dense layer, which is 1 unit. So this is a very simple network, and then you use with an Adam optimizer and a loss of MAE. And what you do is that you you change the batch size to 256, meaning each batch is 256, and then there is an epoch, which is the number of rounds of the training data that you take. It is 10 here. Now, what it means is that when it goes through, it would give off the loss, and it would give off the validation loss. So why is there a validation loss? Is because what we do is here in this when we prepared the data, we we had divided the training data into two parts: actual training data and a validation data, and a frac is 0.7. That means 70% is training and 30% is validation. Next, what we do is that we scale the values so that some value does not dominate over other values, which is a very good technique, because otherwise some values may dominate. That's why you scale the values. So that's the thing. So we have got the training data as well as the validation data. So that's why you see here there is an X train, a Y train, and then there is a validation data, batch size, and the epoch. And one good thing is that once the training is done, the fit method keeps a record of the loss produced during training in a history object. Right. We convert the data to a data frame, which makes plotting easy. So that's why the training history is being converted, and you can see the loss here. So this way you can build a network with stochastic gradient descent. Hope you had understood the concepts. Thank you. Bye.